PD the Polygon Plantain one more time to talk to you about some, I forgot what we're talking about. Trapezoids and kites.
The first vocabulary term is a trapezoid. That's a quadrilateral with exactly one pair of parallel sides. So in our trapezoid ABCD down here, you can see that we only have one pair of opposite sides that are parallel to each other, segment AB or BA and segment DC or CD. These two are parallel to one another. That makes them our bases. Now the legs are going to be the pair of opposite sides that are not parallel to one another. So here that would be segment AD or DA and segment BC or CB. But again, a trapezoid is a quadrilateral that only has one pair of parallel sides. It can't have both pairs. That makes it a parallelogram. Now, an isosceles trapezoid is a trapezoid having two congruent legs. Now, we just said the legs are the pair of opposite sides that are not parallel to one another in a trapezoid. So here that would be segment AD or DA and segment BC or CB. And you see that if those legs are congruent to one another, that makes it an isosceles trapezoid. And that makes sense, right? Because an isosceles triangle has two congruent sides. So an isosceles trapezoid has two congruent legs. Now, a kite is a quadrilateral with exactly two pairs of consecutive congruent sides. Now, they have to be consecutive congruent sides, meaning that if we're talking about consecutive sides, they have to share an endpoint. So here, segment AB shares an endpoint with segment AD. Therefore, they are consecutive sides, and they're consecutive and congruent. Same thing with segment BC and segment DC. They share an endpoint, point C. Therefore, they are consecutive sides. And you see, because they're congruent, they're consecutive congruent sides. Since we have two pairs of consecutive congruent sides, quadrilateral ABCD would be considered a kite. Now let's talk about some isosceles trapezoid theorems. So the first one says, if a trapezoid is isosceles, then each pair of base angles is congruent. So here we have a trapezoid. We know it's isosceles because we see that both of the legs are congruent to each other. And we know from this theorem that if it's an isosceles trapezoid, then each pair of base angles is congruent. Now, base angles are just going to be angles that have the same base as one of their sides. Remember, the bases in a trapezoid are the parallel sides, so that would be segment AB and segment DC. Angle D and angle C would be considered base angles because they both share segment DC as one of their sides. Angle A and angle B would both be considered base angles because they share segment AB as one of their sides. And this is saying if the trapezoid is isosceles, meaning that the legs are congruent, then each pair of base angles is also congruent. So angle A must be congruent to angle B and angle D must be congruent to angle C. Now, the second isosceles trapezoid theorem says if a trapezoid has one pair of congruent base angles, then it's an isosceles trapezoid. So this is basically the converse of the theorem we just talked about, except it says it only needs one pair of congruent base angles to say that it's an isosceles trapezoid. So if we know it's a trapezoid, meaning that one pair of opposite sides is parallel, and we know either angle D is congruent to angle C, or we know that angle A is congruent to angle B, then we can say it's an isosceles trapezoid, meaning segment AD must be congruent to segment BC. Our legs must be congruent. The third isosceles trapezoid theorem says a trapezoid is isosceles if and only if its diagonals are congruent. So if you haven't seen an if and only if statement in a while, it means that it works both ways. So if you have a trapezoid and you know the diagonals are congruent, segment AC or CA is congruent to segment BD or DB, then you know it must be an isosceles trapezoid. Alternatively, if you know you have an isosceles trapezoid, then you know that the diagonals must be congruent to each other. So that's what if and only if means. It just works both directions. If it's an isosceles trapezoid, then the diagonals are congruent. If it's a trapezoid where the diagonals are congruent, it must be an isosceles trapezoid. Now, the Trapezoid Midsegment Theorem says the midsegment of a trapezoid is parallel to each base and its measure is half the sum of the lengths of the bases. So we have a trapezoid, A, B, C, D. Point E is going to be the midpoint of one of our legs, segment AD. Point F is going to be the midpoint of the other leg, segment BC. If I draw a segment connecting those two midpoints of our legs, that is the midsegment. Now the midsegment, according to this theorem, has a couple properties. The first is that it's going to be parallel to each of the bases. So segment AB is parallel to segment EF, which is parallel to segment DC. So our midsegment is parallel to each of our bases. Its measure is also going to be half of the sum of each of the bases. So if I take the measure of segment AB, add it to the measure of segment DC, and then divide that sum by 2 or multiply it by half, I will get the measure of segment EF, our midsegment. Now let's talk about some kite theorems. So the first one says if a quadrilateral is a kite, then its diagonals are perpendicular. So we have two diagonals in our kite here, segment AC or CA and segment BD or DB. And you can see, because it's a kite, the diagonals are going to be perpendicular. They're going to intersect at a 90-degree angle. So segment AC is going to be perpendicular to segment BD. Now the second kite theorem says if a quadrilateral is a kite, then exactly one pair of opposite angles is congruent. The angles that are going to be congruent are going to be formed by two non-congruent sides. So segment AD and segment DC are not congruent. They form this angle right here, angle ADC, that is congruent to angle ABC up here, formed by segment AB and segment BC, which are not congruent to one another.
Gonna split! It's example time!
Now example 1 says find each measure or value given the isosceles trapezoid below. Round to the nearest tenth if necessary. So here we have an isosceles trapezoid and we are trying to find the measure of segment QS. So where is the measure of segment QS? That would be right here, 9x minus 15. So in order to find the measure of segment QS, I clearly need to figure out what x is. So that's going to be my first step. So to find x, I need to set up an equation where I can solve for x. So where's another x in this problem? Ooh, that would be right here. That would be the measure of segment RT. Well, what do I know about the diagonals of an isosceles trapezoid? Well, I just learned a theorem that said the diagonals of an isosceles trapezoid must be congruent to each other. So segment QS must be congruent to segment RT, meaning that the measure of segment QS has to be equal to the measure of segment RT. So then I can take what those measures are equal to, 9x minus 15, I can plug that in for the measure of segment QS, and then 4x plus 12, I can plug that in for the measure of segment RT. When I do that, I can then solve for x. So here, to solve for x, I subtract 4x on both sides, add 15 to both sides, divide both sides by 5, and I get x is equal to 5.4. But I'm not done. I'm trying to find the measure of segment QS. What is the measure of segment QS? Well, we said it's 9x minus 15. So I can then take what I found x to be, plug it in for the measure of segment QS for x, and then simplify. 9 times 5.4 is going to give me 48.6. I then subtract 15, and I get 33.6. That would be the measure of segment QS here. Part B, I'm trying to find the measure of angle STQ. So angle STQ would be right here. So its measure is 6y minus 11 degrees. So I clearly need to figure out what y is. So my first step is going to be to find y. So how do I set up an equation to solve for y? Well, I see that the y's are only in our angles here. Well, what do we know about the angles of an isosceles trapezoid? Well, I know that the base angles of an isosceles trapezoid have to be congruent. So if the measure of this angle right here is y plus 14 degrees, then its other base angle over here must also be y plus 14 degrees. Down here, we know that this base angle is 6y minus 11 degrees, meaning that its other base angle must have a measure of 6y minus 11 degrees also. So now, because a trapezoid is just a quadrilateral, a four-sided figure, I know that the sum of the measures of the interior angles must equal 360 degrees. So I'm going to add up the measures of all of the interior angles of this trapezoid and set it equal to 360 degrees. I can then take what each of those measures are equal to and plug them in over here, and then I can solve for y. So how do I solve for y? Well, I'm going to combine like terms. 6y plus y plus y is going to be 14y, and then negative 11 plus 14 plus 14 is going to be positive 6. I then solve for y by subtracting 6 on both sides, dividing both sides by 14, and I get 354 over 14, which I can simplify to 177 over 7. Now notice, I did not round this to the nearest tenth. You only round your final answer to the nearest tenth. Here, that would be the measure of angle STQ. So what we're going to do is keep this as exact as possible until the very end. That's when we're going to round. If you round too early, you'll get the wrong answer. So here, I'm going to take the measure of angle STQ, which we said earlier was 6y minus 11. I then take the y value that I found, which is 177 over 7, plug that in for y here, and I can simplify. 6 times 177 over 7 minus 11 is going to give me approximately 140.7 degrees. Notice here is where I rounded to the nearest tenth, the very end.
Ooh-wee! Time for you, Trent!
Okay, doing the same thing here. So we want to find the measure of segment BD. So where's the measure of segment BD over here? That would be this measure right here, 2x plus 8. So in order to find the measure of segment BD, I clearly need to find x first. So how do I find x? Well, I need to set up an equation to solve for x. So where's another x in this problem? That would be here, the measure of segment AC. So how are these then related? Well, I know this is an isosceles trapezoid, so based on one of the theorems we talked about earlier, the diagonals of an isosceles trapezoid must be congruent. So segment BD must be congruent to segment AC, meaning that their measures must be equal to each other. So what I can do then is take what their measures are equal to and plug them in over here. The measure of segment BD we know is 2x plus 8, that's going to go in here, and the measure of segment AC is 6x minus 7, that's going to go in here. I then solve for x. There's a bunch of different ways to do this. I'm going to subtract 6x on both sides, subtract 8 on both sides, divide both sides by -4, and I get x is equal to 3.75. Now, what am I trying to find? I'm trying to find the measure of segment BD, so I'm not done. I'm going to take the measure of segment BD, which we said was 2x plus 8. I take the x that we just found, plug it in the measure of segment BD for x, and I simplify. 2 times 3.75 is going to give me 7.5. Add that to 8, and I get that the measure of segment BD is 15.5. Part B, we want to find the measure of angle DAB, which is this angle right here, whose measure we see is 5y plus 4. So I clearly need to find y first. I can then plug that in and get the measure of angle DAB. So how do I find y? Well, I need to set up an equation to solve for y. So where's another y in this problem? That would be in this angle down here. And you see that the y's are in the angles, so I need to set up an equation with the angles. Now we said in an isosceles trapezoid, the base angles must be congruent to each other. So if the measure of this angle right here is 5y plus 4 degrees, then the measure of the other base angle must also be 5y plus 4 degrees. The measure of this base angle is 10y minus 15 degrees. Then the measure of the other base angle over here must also be 10y minus 15 degrees. Once I've found all of the measures of the interior angles of this quadrilateral, this trapezoid, I can set up an equation now to solve for y. So how do I set up that equation? Well, I know that the sum of the measures of the interior angles of a quadrilateral has to be 360 degrees. So I can say that the measures of each of these interior angles added together has to be equal to 360 degrees. I can then take what these measures are equal to, plug them in to their respective spot over here, and I can simplify. 10y plus 10y plus 5y plus 5y is going to give you 30y. Negative 15 plus negative 15 plus 4 is going to be negative 22. I then solve for y by adding 22 on both sides, dividing both sides by 30, and if I simplify this, I end up getting y is equal to 191 over 15. Again, don't round too early. Leave your variable as exact as possible so that when you plug it in to find what you're actually looking for, the measure of angle DAB, I will get a more exact answer. So here, to find the measure of angle DAB, I take what that's equal to, which we said was 5y plus 4. I then plug in the y that we found, which was 191 over 15 for y down here, and I simplify. 5 times 191 over 15 plus 4 is going to give me approximately 67.7 degrees if I round to the nearest tenth. Now, example 2 says find each measure or value given the kite below. So this time we're dealing with a kite, and we want to find the measure of segment AB. So the measure of segment AB would be this segment right here. Okay, so what do? Well, what do we know about a kite? Well, we know it has 2 pairs of consecutive congruent sides, but that doesn't really help us because we want to find the measure of segment AB, and we don't even know the measure of segment AD. Otherwise, that would have been really easy. Well, we also know that the diagonals of a kite are perpendicular to one another, so this must be a 90-degree angle in here. Does that help us? Yeah, it actually does, because if you look over here, we have a right triangle, and we know two sides of that right triangle. We just need the third side, which would be segment AB, which is what we're trying to find. So how do we find the third side or missing side of a right triangle? We use the Pythagorean theorem, and the Pythagorean theorem says a squared plus b squared is equal to c squared. You square each of the sides, add them together, and set it equal to your hypotenuse squared. So which ones are the legs? Which one is the hypotenuse? The hypotenuse has to be your C value. It has to be the side that is opposite the 90-degree angle. So that would be segment AB in this case. The other two, it doesn't matter which one's A or which one's B. So in this case, segment AE we'll say is our A value, segment BE we'll say is our B value, and then segment AB is going to be our C value. Now all we have to do is plug in what we know. We know that the measure of segment AE is 3 inches, so that goes in here. We know the measure of segment BE is 4 inches, that goes in here. And we're trying to find the measure of segment AB. So let's simplify this. 3 squared is 9, 4 squared is 16. We then add those together and we end up getting 25. To get the measure of segment AB, we square root both sides, and we get that the measure of segment AB would be 5 inches. Sweet, all done. Let's move on to the next one. So part B, we're trying to find the measure of angle BCD. So angle BCD would be this angle right here. How do we find this angle? Well, if you recall, a kite has one pair of congruent angles, and those are the angles formed by the non-congruent sides. So that would be this angle right here formed by the non-congruent sides, and then this angle over here formed by the non-congruent sides. So if we know angle ADC has to be congruent to angle ABC, and we know the measure of angle ADC is 75 degrees, we know the measure of angle ABC up here must also be 75 degrees. Now, all we have to do in order to find the measure of angle BCD down here is set up an equation where we add together the measures of the interior angles of this quadrilateral, this kite, and set it equal to 360 degrees, because we said earlier the sum of the measures of the interior angles of a quadrilateral, a four-sided figure, has to be 360 degrees. So now I just take what these measures are equal to. The measure of angle ABC we said is 75 degrees, that goes in here. The measure of angle DAB is 130 degrees, that goes in here. The measure of angle CDA would be 75 degrees, that's going to go in here, and we're solving for the measure of angle BCD. So let's simplify this. 75 plus 130 plus 75 is going to give you 280. We then subtract that on both sides. We get the measure of angle BCD has to equal 80 degrees. And you're done. Okay, doing the same thing. This time we want to find the measure of segment CE. So where's segment CE? That would be right here. Interesting. We're not even given anything for that measure. So how do I do this? Well, again, we have a kite, and we know that the diagonals of a kite are perpendicular, meaning that they meet at a 90-degree angle. We also saw in the last example that this then breaks up the kite into 4 different right triangles. This right triangle over here is the one I want you to focus on. Here we know 2 of the side lengths. We know this side right here is 2 feet, and this side over here is 6 feet. The side that we're looking for, segment CE, we don't know. That's the only missing side length of this right triangle. So how do we find a missing side length of a right triangle? We use the Pythagorean theorem. So we're going to go a squared plus b squared is equal to c squared. Your a and your b value, it doesn't matter which one is which. I can say the measure of segment BE is going to be my a value, and the measure of segment CE is going to be my b value, or vice versa. Your c value has to be your hypotenuse, the side that is opposite the 90-degree angle. So that would be the measure of segment BC. So in this case, I'm going to go the measure of segment BE squared plus the measure of segment CE squared has to be equal to the measure of segment BC squared. That's my Pythagorean theorem. Now, I'm going to plug in what I know. I know the measure of segment BE is 2 feet. That's going to go in here. The measure of segment BC is 6 feet. That's going to go in here. I then solve for the measure of segment CE, which is what I'm trying to find, by simplifying. 2 squared is going to be 4. 6 squared is going to be 36. I subtract 4 on both sides, square root both sides, and I get the measure of segment CE has to be equal to the square root of 32. Now, I don't want to leave this rad 32 if I can simplify this. Is there a perfect square that goes into 32? Yes, 16 does. So I can break this up into rad 16 times rad 2. I chose 16 because it's a perfect square, and the square root of 16 we know is 4. Rad 2 stays rad 2. You can't break that up any further. So you know that the measure of segment CE has to be equal to 4 rad 2 feet. Part B, we want to find the measure of angle CDA, which would be this angle right here. So clearly we have to figure out what x is first. Then we can just plug it in and find the measure of angle CDA. How do we find x? Well, we need to set up an equation to solve for x. Where is there another x in the problem? Well, there's one here. So it's looking like we need to set up an equation based on the interior angles of this kite. Well, we said a kite is a quadrilateral, so we know that the sum of the measures of the interior angles of a quadrilateral has to equal 360 degrees. Well, I need to figure out this angle though, if I want to do that. What is the measure of this angle? Well, we know a kite has one pair of congruent angles, and those would be the angles formed by the non-congruent sides. So this angle right here, angle CDA, and this angle up here, angle ABC. We know those must be congruent, therefore their measures must be equal. Now I can take the measures of each of the interior angles here, add them up, and set it equal to 360 degrees. Now we plug in what each of these angle measures is equal to, and we can simplify. 4x plus 7x plus 7x is going to give you 18x. Negative 6 plus 120 plus negative 6 is going to give you 108. We then solve for x by subtracting 108 from both sides, dividing both sides by 18, and we get x is equal to 14. Now we're going to take that and plug it in for the measure of angle CDA, which is what we're trying to find. We said the measure of angle CDA is 7x minus 6, so we take 14, plug it in for x, simplify, and we end up getting that the measure of angle CDA has to be equal to 92 degrees. Now, example 3 says for trapezoid FACD, E and B are the midpoints of the legs. If the measure of segment FA is 12 meters and the measure of segment DC is 22 meters, find the measure of segment EB. So the first thing we want to do is label our figure over here. We know that points E and B are the midpoints of our legs, segment AC and segment DF. So if we want to label that, we just say that since B is the midpoint over here, that these two segments must be congruent. If E is the midpoint over here, then these two segments must be congruent. We also know that the measure of segment FA right here is 12 meters and the measure of segment DC up here is 22 meters. We are trying to find the measure of segment EB in here. Well, if you recall, in a trapezoid, if you have a segment joining the two midpoints of the legs, this is technically called your midsegment. And one of the properties of the midsegment is that its measure is equal to half the sum of the two bases. So if I want to find the measure of segment EB, what I'm going to do is add together the measures of the two bases, the measure of segment FA and the measure of segment DC, and then divide that by 2 or multiply it by half. So let's do that. The measure of segment FA we know is 12 meters. That goes in here. The measure of segment DC or CD is 22 meters. That goes in here. We add those together, multiply it by half, and we end up getting 17 meters for the measure of segment EB, our midsegment. Now, example 4, very similar to example 3, we have a trapezoid. We know Q and R are our midpoints of our given legs, segment LO and segment MN. So we want to label that as such. If we know Q is the midpoint over here, then we know this segment must be congruent to this segment. If we know R is the midpoint over here, we know this segment must be congruent to this segment. Now let's also label what else we're given. It says if the measure of segment LM is 6y, so the measure of segment LM must be 6y. Measure of segment ON must be 11y, so we put that here. The measure of segment QR, it actually gives us our midsegment. It's 152. So we're trying to find then the measure of segment LM, measure of segment LM up here, which we know is 6y. So in order to find the measure of segment LM, we clearly need to find y. So how do we set up an equation to solve for y? Well, we just said in the last example that if we have a segment joining the midpoints of our legs in a trapezoid, that is called a midsegment. And one of the properties of the midsegment is that its measure is equal to half the sum of the two bases. So we can set up an equation to solve for y based on that fact. We can say that the measure of our midsegment, segment QR, has to be equal to 1/2 the sum of the measures of our two bases, segment LM and segment ON. Now we plug in what each of those things are equal to. The measure of segment QR is 152, that goes in here. The measure of segment LM is 6y, that goes in here. And the measure of segment ON is 11y, that goes in here. Now we can simplify this and solve for y. So 6y plus 11y is going to give you 17y. There are then two ways you could solve this for y. You could either multiply this 1/2 to the 17. You get 8.5y is equal to 152. Divide both sides by 8.5. But then you can't have a decimal in a fraction, so you multiply the numerator and denominator by 10. And then you can simplify simplify, but that's a little more complicated. Easier way to go here would be to get rid of this 1/2 by multiplying both sides by 2. If I multiply this side by 2, the 1/2 and the 2 cancel each other out. Over here, 152 times 2 gives you 304. I can then solve for y by dividing both sides by 17, and I get y is equal to 304 over 17. Notice that I did not round because I'm trying to find the measure of segment LM. That means I need to keep what I found for y as exact as possible, because if I round too early, I'll get the wrong answer. So I then find the measure of segment LM by taking what the measure of segment LM was equal to, 6y, plugging in what I found for y here, and then simplifying. 6 times 304 over 17 gives you approximately 107.29. We rounded here to the nearest hundredth because this is what we are trying to find.
Aren't you glad I didn't say, you try?
Okay, doing the same thing here. So here we have trapezoid FACD, where E and B are going to be the midpoints of our legs. Now remember, the legs are the non-parallel sides. So that would be this side and this side right here. So if E is the midpoint over here, we can mark that up where this segment must be congruent to this segment. We can also mark up down here, if B is the midpoint over here, we can mark that this segment must be congruent to this segment. We also need to mark up a couple other things. The measure of segment FA is 4x minus 2, so we're going to put that here. The measure of segment EB is 6x plus 7. That's going to go here. And the measure of segment DC is going to be 9x plus 12. That's going to go down here. Now we're going to find the measure of segment EB, which we know, again, is our mid-segment because it's the segment in a trapezoid that is connecting the two midpoints of our legs. So how do I find the measure of segment EB? Well, it's equal to 6x plus 7. So I clearly need to find x, and then I can just take that and plug it in here. Well, how do I find x? Well, I need to set up an equation that allows me to solve for x. So how can I set up an equation based on these three segments? Well, we just said that the measure of the mid-segment is equal to 1/2 of the sum of the measures of the two bases in your trapezoid. So what I'm going to do is I'm going to create an equation where I have the measure of my mid-segment, segment EB, is equal to 1/2 the sum of the measures of my two bases, segment FA and segment DC. What I can then do is plug in what I know these measures to be. The measure of segment EB we know is 6x plus 7. That's going to go in here. The measure of segment FA is 4x minus 2. That goes in here. And the measure of segment DC is 9x plus 12. That goes in here. Now I can simplify and solve for x. So how do I simplify this? Well, I need to start with the parentheses over here. 4x plus 9x is going to give me 13x. Negative 2 plus 12 is going to be positive 10. Now, how do I solve this? Well, there's two things you can do. One would be to distribute this 1/2 to the 13x and to the 10. But a little easier for me is to multiply both sides by 2. If I multiply both sides by 2, the 2 and the 1/2 just cancel each other out, and I'm left with 13x plus 10 over here. Over here, when I multiply by 2, I have to distribute the 2 to the 6x and to the 7. When I do that, I get 12x plus 14. Now I can solve for x. So I just subtract 12x from both sides, subtract 10 on both sides, and I get x is equal to 4. But I'm not done. I want the measure of segment EB. We know the measure of segment EB is 6x plus 7. So all I have to do is take what I found x to be, 4, plug it in up here for x in the measure of segment EB, and then simplify. 6 times 4 is going to give me 24, plus 7 is going to give me 31. So the measure of segment EB then would be 31. Now example 5 says, given ABCD is an isosceles trapezoid, we want to prove that angle DAC is congruent to angle CBD. So the first step in a geometric proof is to mark up the figure with the given information. So what are we given? We're given that ABCD is an isosceles trapezoid. Now this doesn't say anything is congruent to anything else yet, but we will be able to use this information in a second when we game plan, when we figure out how we're going to get from what we're given to what we're trying to prove. But in the meantime, we'll move on to step 2, which is to state our given. We are given that ABCD is an isosceles trapezoid, and the reason for that, it's given. Now, step 3 in a geometric proof is to come up with a game plan. How are we going to get from what we're given to what we're trying to prove? Well, I'm trying to prove that angle DAC, this little angle right here, is congruent to angle CBD, this little angle right here. Well, how do I do that? Well, I do have two triangles right here, triangle DAC and triangle CBD. Couldn't I prove that those two triangles are congruent to each other? And then I could say that angle DAC is congruent to angle CBD by CPCTC. Corresponding parts of congruent triangles are congruent. Well, how do I prove these two triangles are congruent? Do I have any information that would help me do that? Yeah, I know ABCD is an isosceles trapezoid. So what do I know about isosceles trapezoids? I know that the legs of an isosceles trapezoid must be congruent. So segment AD must be congruent to segment BC because of the definition of an isosceles trapezoid. I also know that the base angles of an isosceles trapezoid must be congruent. So angle ADC must be congruent to angle BCD down here. Lastly, I know that these two triangles share this given side, segment DC. So I could say segment DC is congruent to itself by the reflexive property. Therefore, in both of these triangles, I have two sides and the included angle congruent to two sides and the included angle. Therefore, these two triangles are congruent by the side angle side congruence postulate. Therefore, I could say that these two angles then would be congruent by CPCTC. So let's do it. First, we said that this segment right here, segment AD, must be congruent to segment BC because they're the legs of an isosceles trapezoid. And by the definition of an isosceles trapezoid, the legs must be congruent. We also know that angle ADC down here must be congruent to angle BCD down here. And the reason for that is because base angles of an isosceles trapezoid are congruent. Next, we said that segment DC must be congruent to itself by the reflexive property. Now we've shown that two sides and the included angle are congruent to two sides and the included angle. Therefore, these two triangles then must be congruent by the side angle side congruence postulate. Lastly, because this triangle is congruent to this triangle, we can say that this angle must be congruent to this angle because corresponding parts of congruent triangles must be congruent. And you're done.